A quick overview here, I pointed four type of modalities. We have molecular data and omics data. So molecular data can be biomarkers coming from very targeted assays, all the way to this large profiling omics platform like proteomics, transcriptomics, genetic data, etc. Imaging, from histopathology, so the digital pathology slides, to CT, MRI scans, or even like pictures, for example, of the skin. A new and more emerging branch is the digital health and medical devices. And this spans from having your electrocardiogram or your EEG, all the way to data coming from your Fitbit or smartphone. And then, of course, the more classical healthcare data. This comes from medical records, doctor notes, laboratory values, prescriptions, etc. So if you might appreciate the variety of data, also means that we have a lot of features. So techniques like dimensionality reductions or representation learning are also quite useful tools in our work. So I've talked about data, I've talked about the problems. Now I just want to highlight a couple of applications of machine learning in translation and precision medicine. And I picked a few examples, mostly based on the different data modalities that I showed, but also to appreciate the variety of machine learning techniques that we use. So the first one is maybe one of the most common questions that we get, of course, because we work with clinical trials, and it's really about identifying the molecular signatures that are predicting of patient response. The scenario here is that we have data, profiling data, like proteomics in this example from a publication from some colleagues, related to patients that are enrolled in a clinical trials where we are testing a new drug. Here, use cases in COPD, so respiratory disease. And while I'm not going to go into the details of the biology or the findings, happy to do so afterwards. But what I want to show is that in this scenario, basically we start with not so many observations, or not so many patients. We are talking about usually in the range of hundreds. But on the other side, we deal with many features. So in this case, we're using proteomics data to predict the signatures. So we really want to reduce the dimensionality of the space from like 5,000 proteins coming from this proteomic platform into really just a short interpretable molecular signature that we can actively use in our studies to understand. So for these scenarios, what I found very valuable is really just using basic classical machine learning models. Here, if you see, we have like linear regression or just hierarchical clustering. And because the interpretability and taking like a fast action when you have like a relatively small data set is just like the best that you can do. Medical computer vision is maybe one of the most mature fields of applied ML, especially because of like really making things faster, and it's really commonly deployed. So here I have a few examples. So on the top you see a publication from some of my colleagues where it's applied to the field of digital pathology. So here what they've done is to learn a histology-specific image representation that actually outperformed ResNets that were trained just on ImageNet, so like a standard big, large imaging database. And this is especially important because it's not only about learning images, not only about segmenting images, but using that information to downstream questions, like, for example, in this case, detecting different types of lesions in a slice. Other cases are, for example, using image segmentation for detecting, for like segmenting areas in a brain MRI, or even classifying skin lesions on a picture taken from a smartphone. In this case, we usually adopt and deploy a lot of methods that are out there in literature, like UNets, but really the purpose is to have them more sensitive and faster imaging biomarkers that we can use in our clinical trials or when delivering care. Last example, which is at the bottom, is actually, maybe you remember this from one of the early slides from Nick. It's using GANs to generate images. And why it's really cool is because then now we can share our data with external collaborations. lately, due to like a lot of connected sensors, smartphones and digital technologies, we can now collect continuous data from patients related to their behavior. Think about physical activity, vital signs, cognitive functions, and a lot of contextual information. This data and this field is related, is known as digital inference, and I think there will be a talk later today on that. What is really cool for clinical development is that we can use this data now, and especially using time series analysis, to convert all these time series, all these very noisy signals coming from patient behavior, and transform it into quantitative, objective, health-related quality of life factors. So here I'm studying a pilot study that we've conducted where we use exactly this type of data to then quantify and predict patient-reported outcomes on fatigue. Maybe we should test it on some of you if you're tired already this morning. And what is important in such a machine learning project is also the interpretability and the feature selection. Because at the end, the objective is not only the classification, but is really defining what are the key measures, the key behavioral measures that are predicting of fatigue in patients. And for the last category, we have many times available these large longitudinal electronic records. These type of data sets usually have tens or hundreds, millions of patients with multiple diseases and tens of thousands of clinical features. Now, why are these important? With this type of data sets, we can really model patient trajectories, we can predict diagnosis, and we can stratify patients. And we also borrow a lot of techniques from NLP for that. One of the applications that I pointed out here is like a preview of a project that we are working on, where we are trying to define a general framework to stratify patients based on their risk of developing other comorbidities, also other diseases, or specific outcomes like death or onset of the tumor. One part that is particularly interesting in this framework is that we have available is the use of a modified version, a standard version of MedBERT, that basically what it does is that you have all these patient trajectories, very complicated, it's a synchronous timeline of each patient, and you convert it into a simplified barcode. So this is really helpful when doing the downstream modeling.